Professor Carlos, he's an assistant professor at Reactive University, in Edinburgh, UK. He's the head of the Robot Motor Intelligence Lab, and he's an expert in the building athletic intelligence for robotics with the legs and arms. So today his topic is about Agile and Perceptive Locomotion in leg robots. Okay, welcome him.
Thank you so much. Let me just try. Everything is here. Okay. Okay. Thank you. Thank you, the organizer, for putting all these speakers and the invitation. So in my today's talk, I'm actually going to talk about model-based control. So we have seen some model-free work in the previous part of the workshop. And actually, I'm going to emphasize my talk in something that we call, in the topic of Agile and Perceptive Locomotion. Let me start. Everybody, probably I don't have to convince you why we need Agile and Perceptive Locomotion. Pretty much we can say that robots are very slow nowadays and very rigid in the way that they adapt. And one of the challenges where we find both fields is model-based and model-free is adaptation of contact timing. So humans are very versatile. Humans are very optimal. They have very optimal gait. And you can see here that we don't have any robot that is close to do this nowadays. And this is one of the big challenges that I see it still remain in these years. Another important aspect is we want robots that can really navigate over really challenging terrains. We have seen amazing results from different labs in the world, but still none of them are able to do what this animal can fantastically do. So it's incredible. And what is important here is to very carefully design or select good location and guarantee stability while considering properties from the environment that we don't know. This is also some of the comments. Some of the previous speakers were talking about this. I really believe that locomotion is not the only thing that we have to think about it, but actually loco manipulation. And we need robots that can select reason about different contact location, and they can perform manipulation and locomotion tasks simultaneously, and this is still remains very challenging. And this is not only for model-based control or model approaches, but also for model reinforcement learning. I really like to think about first principles. In this case, first principles optimization. So I typically call these top-down approaches, things that are and why I really like them is because they provide a structure, they provide guarantee, they are interpretable, so we really understand what is going on. And as a scientist, I really want to understand what I'm doing. So but if you are a person that is more oriented to results, still top-down approaches matter. And this is one example that we have run with our Perceptive Locomotion pipeline. And we know that this example does not work with reinforcement learning because ETH-Folk has reports on results on this. And the reason is because our robot have to navigate through narrow stepping stone conditions. And there's a small region where we can make a footstep. And we know that typically this model-free reinforcement learning algorithms, they don't handle well constraints. And we have a very constrained problem here. So this is one motivation, but also this is a bit more, kind of suggesting and arguable. But I also find difficult that model-free reinforcement learning can do athletic behaviors like we can see in the left figure. Yeah, top down. This is top down. This is, yes, top down. why I think I find it hard to do this with so kind of reinforcement learning model-free approach is because Talus is very limited. It doesn't have all these tremendous actuators, and most of the human robots are like this. And to be able to generate this motion without considering those highly constrained, it's very challenging, even for top-down approaches, but I think it's easier. Another thing is we can seamlessly integrate these techniques for any robot. Actually, my approaches have been also tested in quadrotors and other things, but I'm not reporting in this workshop anything regarding this, but we can, without so many go from one robot to another, as you can see in the case of the quadruped robot. Now, let me introduce you a bit the framework. So our framework is classical, so I won't say that is what is unique is how we solve all these models. So first, we have a robot that is navigating and building a robot-centric map, and also building a robot-centric set of combat regions, as you can see there, and making decisions with this. So when we talk about perception, we talk about combat regions in this talk. And this is the pipeline. We have the terrain elevation, providing the high map. We segment the planes. We use these planes to select footstep regions, or what we call region selection algorithm. And then we are adapting footstep location very fast and sending this reference to our MPC. Most of my talk is going to be about inverse dynamic MPC, but actually we can do also for forward dynamics MPC. And when I say forward, is whole body dynamics. And this is what is unique from our work. And also because I'm focused on inverse dynamic, because I'm not aware of other inverse dynamic paper MPC work in the literature. You can see a bit how the frequencies go, but actually in a nutshell, so we have an MPC or these green blocks that runs at 50 Hz or 100 Hz can run at 100 Hz, and then we have the region selection that runs at 10 Hz. Let me explain to you all these models first. So as I said, perception is through combat region in this talk. So one of the important things that we have to do is to reduce the information of the combat region. And the reason is because we need to do this in real time, and we are running, this is a combinatorial problem, difficult to run in real time. So here we use the BW algorithm, as you can see here, to reduce the number of nodes or vertices in this description. And also the other thing what we need to do is, because combat region, they can be overlapping, they can also not be combats in reality. So we have to make combats first, and then we need to remove everything that is overlapping, because we know that a region that is over another probably won't make a footstep. So here you can see a plot, a figure where we are building this non-combat regions into a 3 regions. I don't remember, these are the green ones. Yeah. And here is a video where you can see, this is real experiment where we can see how animal is building this combat region while crossing this. It's a pallet with some goods. It's like crossing a river. That's the whole idea. And we have some narrow also goods like 10 centimeters width. Yeah, we can compute this online. Now, once we describe the regions or the terrain into regions, we want to select what regions we want to navigate through and the footstep locations within those regions. The first thing that we do is based on the user intention, so is that joystick, we can sample an expected COM motion based, again, on the velocities that we are commanding. But we need to sample this around a terrain where it's full region. So, and we don't know actually the COM's high position. So what we are doing here is taking all this, taking the expected COM motion and fitting this within the combat region. This is just a classical QP problem, so which I'm gonna skip it because it's not that interesting. Now, when the other thing that we have to do is when we have this expected motion of the COM or path, I will say path, we want to ensure that our robot can go through locomote through these obstacles. And the way we do here is with kinematic feasibility. So it's this range of motion, this ROM thing that we have here. So this is actually another video from a real experiment where we can see how we are building this range of motion regions in green. And actually, what we do here is we analyze it offline, the full kinematics, and we make a convex tool of the full kinematics. Because you will see later, but we want to formulate this problem using a mid-set integrate convex optimization. So what we are doing here is again taking and selecting these footstep regions that are kinematically feasible. This problem actually, as I just mentioned, is a mid-set integer quadratic program, and you can see it in the equation there. So where our goal is to find the footstep, the sequence of footstep position, and we want this capital P, and we want this capital P be within some regions that we have extracted from the perception system, and that's our encode without the green box. That's actually an if conditional. So what it means that the equation is we want to select one particular region and not all of them. So that's why it's combinatorial, this problem. What we do is the classical approaches of mid-set integer. We formulate this using the pick M notation, which I'm not gonna go through this nitty-gritty aspect, but this is, trust me, if you don't know, this is the classical way of doing things here. And also, I wanted to mention something that I forgot. When we select this region, we want to make sure that the robot can reach that region, and that is with again the range of motion constraint that actually is this inequality constraint we have here, which is K capital P and lower than just small k. That is actually the thing. Another thing is so we want to select this regions using some criteria. The criteria here is Rayber heuristic criteria. So given the intention of the user, we can compute where Rayber wants to have the footstep location, and we try to choose as much as possible that. Just for the ones that are not familiar with Rayber, heuristic is actually sort of encoding a lower dimensional system of the dynamics. I think it's a linear pendulum, I think. What I have to do is, or what we do is we still following the Rayber heuristic, because we can have events like we are pushing the robot or things like that. So we want to adapt these footstep regions, and also the user might change intention. So the joystick command reference can change. And how we do this is basically solving this simple quadratic program, which we can do it very fast. It's very simple. And here there's not any combinatorial problem because we already know what is the region that we want to do. We want to navigate through, and that's encoding the equality constraint that you can see here. And we want to, again, follow this Rayber heuristic, which is this equation here that I'm gonna just skip, but basically, yeah, you can see the reference velocity and angular velocity. These are information from the user. Another important thing is we want robots to navigate through terrains like this. That means that we need to ensure that the robot won't collide with the environment. And again, this is another real experiment, no simulation here. How we do this is basically we are deforming a Bezier curve. The curve is, we provide a reference curve. This is the red curve. And through this convex region, we can build a hyperplane, as you can see in red, and actually find a Bezier curve that avoid that obstacle. This is another simple copy problem that can run very, very fast, and actually we run very fast. And what we have here is basically this region of motion in green, and also the initial and terminal constraint. So this is a bit very classical, I will say. Probably what it is a bit more interesting here is how we do MPC. So we follow the hybrid dynamics paradigm. Basically, this framework describes any motion through different contact modes, and you can see in each of these phases contact mode. This is a diagram for a biped, by the way, where the gray areas are areas where we have contact, and the other one are where we expect a swim motion. And again, so we are predefining this timing. So there's very tight, unfortunately, but that's how we are doing here. And in the formalities of hybrid dynamics, we want to connect these modes of dynamics through reset math. And that's what you can see between the phase 3 and 4. We got this reset math capital delta, which actually is an impulse dynamics. And we, generally speaking, these MPC have to solve very large decision problems in very few milliseconds. So we are talking about 12 or even 10, 20,000 decision variables. So this is the problem. So we have these hybrid dynamics are encoded in this equation that you can see, and they also we impose stability through friction cone or grain cone, and tracking the reference through the contact placement. Our cost functions are nonlinear, but they just regularize the problem using some nonlinear cost function, and actually they don't provide so much insight. That actually, when we were generating this humanoid, we were not really telling the behavior of the robot. And through this formulation, we can go through, we can generate many motions, even dynamic motions, as you can see, this jumping case in simulation. Now, let me explain you why inverse dynamics. So the reason why we invest in developing an inverse dynamic MPC is the high convergence that have this, or a bit higher convergence that have when compared with forward dynamics. In a nutshell, it's because we distribute the nonlinearities. And let me explain you. So you have an integrator. I mean, your dynamics, your discrete dynamic can be seen as an integrator function and some kind of continuous dynamics. And that's the green equation that we see here. This is a Red-Courses Newton-Euler algorithm that very, very popular for computing inverse dynamics. But the problem here is now we have to incorporate this extra decision variable, the acceleration, making the problem larger. But the good thing is here is we decouple these two functions. And also another thing that we could remark here is when decoupling these two functions, we can also say that there's tighter, it's not that tight, the integration step that we use compared with the dynamics. So that means that we can typically do coarser optimization. So it means we can discretize the trajectory in larger integration steps. And this has been reported by others and also applies to our algorithm. And a third reason why people might want to go in through inverse dynamic MPC is because they are cheaper to computation for RNA. RNA is much, the algorithm complexity is lower than the algorithm complexity of forward dynamics. And same for derivative. And you can see some reference here that you can go through and understand why this algorithm complexity is lower. But actually, what I can tell you, when you want to compute inverse dynamics, the forward dynamics, you need to compute somehow the inverse dynamics of the RNA. So yeah, that's one reason why we want to do inverse dynamic MPC. However, you might ask why people is not doing inverse dynamic MPC, because there are important challenges, numerical optimization challenges, and that's not obvious how to deal with them. So forward dynamics instead, it fits naturally to any optimal control algorithm like the famous DDP that many people is doing, or our multi-shooting version FTDP. So, and the reason is because we can take some forward dynamics like the ABA algorithm, and embed it inside the integrator and so on. We don't have to handle any equality constraint. And the DP already does that for you. And even if you want to impose constraint, like contact constraint, you can use the Gauss principle of least constraint to develop a dynamic system, a forward dynamics that produces acceleration subject to some constraints. And therefore, you can still use DDP. However, as I said before, when we have an inverse dynamic MPC, we need to handle this equality constraint that we can see in the left, the far left bottom equation. And this is our RNA constraint. Additionally, we are imposing another decision variable, which are the generalized acceleration, which increases the algorithm complexity, increases the computation time of this. And this is already forward dynamics is challenging. And even if we want to consider contact, now we have the contact forces as well. So in practice, just including acceleration, this extra decision variable, acceleration and contact forces for the typical MPC horizon that we use will be something like 6,000 more decision variables, something like a 30% more of decision variable. So it's very challenging again to compute this in real time. Now we start to look in the structure of this program and see how we can exploit this and compute efficiently this. And I'm gonna present you some ideas of how we do this. The first is actually we can condense the inverse dynamics. And let me explain you what that means. This is the linearization of the inverse dynamics, where we consider also attrition dynamics. And what we can do is recognize that the first row is the inverse dynamic and the second row is actually an acceleration-based holonomic constraint of the content. But if we assume that HID, so the infeasibility of the inverse dynamic, is always zero, an assumption that actually we test through a broad range of problems, not only quadrupeds, and it works well. So actually, almost as well. There are a few cases where it might not work that well, but most of the time works really well. So actually we can condense this equation. Condensing means we can reduce some decision variables. And now if you pay attention in the green matrix, you can see that we remove the generalized torques as a decision variable here. That means we have a lower dimensional problem, yet correct. Another important observation, and probably the less obvious observation here, because it comes from understanding numerical optimization. So what I cannot go through this equation and explain you where it comes, but I can tell you that this equation is exact. So when we apply the dynamic or Bellman principle or dynamic programming, what we can do in trajectory optimization is we can actually solve a sequence of the model problem and basically solving this linear system of equation that typically is called KKT. But this is a KKT problem for a state, for one single node. And we have to do this in a sequence of nodes. So what I want to explain to you is briefly, so you can understand this equation here. We have the Hessian of the cost, we have the Jacobian of the constraint, which are these HSU, and the Jacobian of the dynamics. And this is connected with the value function derivative or approximation, which is BX and BX. And another typical thing that we do in DDP is we condense again this. So there's a lot of math here to make this work efficiently. These equations start to be more familiar to the DDP ones if you are familiar with DDP. And now we have this Q function, which is a local approximation of the action value function. But it's the action value function subject constraint, and these are this HU. And because we are talking about constraint problem, one key observation is we can parameterize this control into its rank and null spaces. And this is what you can see in this equation. And to do that, you need to do a rank revealing the composition. If you parameterize this and inject this into the condensed equation of DDP, actually we can reduce this equation and we can remove the augmented Lagrangian and actually this equation. But there's no free lunch here. We need to run a decomposition, which is expensive. So like a QR decomposition. But what we can see is the QR decomposition can be computed in parallel. Actually, all these green terms that you see here can be computed in parallel. Then this is a plot that shows how we reduce the computation time. So actually, we can reduce up to 45%, I think. And we test this across different examples, not only quadrupeds, but also humanoids. But in practice, what you can see is when we have a short complement, so an approach that does not parameterize the controls, the classical approach, we can see that the MPC cannot run as fast as needed. And then it does not guarantee the stability because, again, it's doing computation that are dilated. Another key observation is about feedback MPC. A lot of folks are doing even in reinforcement learning. So when they couple this with PD controllers, a lot of folks what doing is hard coding a whole body instantaneous controller. That in practice or theoretical means you are putting your own policy. So because you tune that. Now, in trajectory optimization, and also I believe in reinforcement learning, you can extract that policy. But in the case of trajectory optimization, that policy is encoded in these feedback gains. For the inverse dynamics, we have decision variable, if you did not realize, are the general acceleration and the contact forces. But these are policies that, given an error in the state, this delta H, we make changes in the acceleration or contact forces. But the way that we interact with robots is through torques, right? So we can composite these two functions, so this policy with inverse dynamic, in the optimal solution, and actually get the joint torque policy. Again, so what it means here is giving an action, our MPC is telling you not what is the optimal trajectory you want to track, but it's the optimal adjustment that you need to do, obviously locally, because we are computing derivatives. So this is an experimental. This is an example where we deactivate the footstep planning. So this is all MPC. There's no footstep that is dealing this, and we're pushing the robot quite strongly. I know it doesn't look, but I'm really pushing quite strongly the robot. And so when this happens, you can see, unfortunately, sorry, you cannot see, but when this happens, what is happening here is the MPC is dealing between feasibility and optimality. It's sometimes sacrificing the feasibility of the motion in such a way to have a kind of numerical optimization around a nice landscape. And this is an example. This is a plot from this experiment where every time that we push the robot, we get an increase in the infeasibility of the dynamics. That's the right plot. So you can see that the dynamics can even go over numbers like 1/9. Some people or some folks might think, oh, but this is not really nice, but trust me, it is what you want when you do numerical optimization. Because this is a numerical optimization problem more than a control problem, we want to really take advantage of what we understand from numerical optimization. Fit and MPC not only balance optimality and feasibility, and that held also the MPC to keep iterating in a really good landscape, but actually in practice can provide some the best tracking that I've seen in my career. When we talk about angular momentum tracking, so we have this looks almost a simulation, but it's not a simulation, it's from this experiment. So the angular momentum tracking is amazing, but also the foot swing tracking, which I'm not reporting in the talk. And the reason why tracking an angular momentum is difficult is because there are some non-holonomics inside the dynamics, and the non-holonomics cannot be easily handled with an instantaneous action. We need to look ahead. So this is another example where we are not able to generate if we don't consider full dynamics and if we don't do feedback MPC. Won't be possible to do this. Here, what I'm showing you is a sequence of jumps, multiple jumps. Why doing multiple jumps is quite hard is because when you are jumping and you land, one jump is simple, but multiple jumps is hard. Because when you land, you want to land in the right posture to be able to jump again. We are not changing the timings like Boston Dynamics doing, so that's why we really need a very good tracking. And the feedback MPC is doing this for us. And you can see how the MPC is updating here. So there's not any reference. The MPC is actually figuring out all this motion. We are not really providing any posture or one starting. And these are the feedback gains you can see in this experiment that they change depending on the time of the controller of the robot. With full dynamics MPC, we can really push the limit of the robot where constraints matters. And this is one example where animal B is crossing this stair with this gap. Actually, this is very challenging. I haven't seen Boston Dynamics or Animal C, which is much stronger than this robot, to achieve this. But it's particularly challenging on Animal B, this black guy here, because it's weaker than many weaker in terms of what the actuators can do, compared with many robots, including the unitary robots. So this is not trivial to do it. And as you can see in the video, so there are cases where the robot is almost reaching the kinematic singularity, so we can actually push the limit of what the robot can do here. And we are all actually reaching torque limits in several instances of this motion. Another example is going through this bot where the bot is as high as the animal. So this is, again, very challenging for animal robot, in general for any robot, and because we are all many times very close to the kinematic limits. And as I say, my hypothesis here is when you are very constrained, your reinforcement learning policy might start to struggle. Another thing is, I say, well, we can use this in different robots. This is the Nadia human robot from HNC, where I also work with. So with HNC, what we want to do is make Nadia the most athletic robot in academia. This is one example where we can generate a running gait, and you can see how the MPC is updating. So first, it's like sort of the robot is falling down, but the MPC is adjusting this, and this is due to our sort of multiple shooting, very efficient way of dealing this, which I'm not presenting here. But we can actually perform jumping tasks, like forward jumping tasks here. And again, you can see how, and this is in slow motion, you can see how the MPC is doing, so taking this. In most of these experiments, the MPC horizon is 1 or 1.2 seconds. Now we are working in much efficient version that we hope we can go over 2 seconds of horizon optimization. And yeah, this leads to some new algorithm for optimal control that we are at the moment developing. So this is all that I have for you here. I really want to encourage you to try our code in Crocodile. We are making a great effort to make this software efficient, and you don't have to invest time on understanding this. You can plug in your application. And yeah, I want to thank you for being here with me. And this is one example that we use it for running our framework in the ICRAF challenge on this year in London. Thank you.